loud. And there we go. Okay, so what I'm going to do in this drawing is I'm not going to go through every single little detail because I just can't possibly draw that much. And also we got about 20 minutes left. Okay. So let's just, I'm going to establish some rules up here. Because it sounds like one of the concepts that may not be super solid as far as how all this works. And again, going back to the importance of order of events and delays, tying the depolarization events to the contractile steps of the heart is what we're really going to try to do here. But the overarching principle that you really need to remember to understand any of this is this sort of central axiom of any muscle, and that is depolarization happens before contraction. So if you want a muscle fiber to generate tension and get shorter, you have to have its membrane depolarize first. Which means that the electrical changes of the heart that we just discussed, so things like the depolarization waves spreading across the atria, that's just talking about depolarizing, so sodium going into muscle cells. So the electrical changes of the heart are followed by contraction. So there's a chart in your book. Oh my goodness, my budgie is screeching because she doesn't like the leaf blower man. Stig, be quiet. That's not gonna work. So if you look at the EKG, for example, on the chart in your book where it has, it's a figure. It's a big, huge full page guy. It's got the EKG at the top, and then it has pressure and volume changes in various portions of the heart below it. That's the one I'm talking about. If you look closely at how atrial depolarization and atrial contraction line up with the EKG wave, you'll notice some things. So let me draw you a EKG wave first.
We can't see your drawing.
That's weird. Oh, I see it. Okay. There we go. Can you now?
Yeah.
Okay. So depolarization happens before contraction, and electrical changes of the heart are followed by contraction. So let's label our EKG wave first. P, Q, R, S, T. So if I was going to draw a line indicating where atrial contraction started, where would I draw the line? And I've asked students to do this before on short answer tests. We don't have that as part of the online experience because I can't grade that many, unfortunately. But so often I'll have a question where I'm like, hey, draw an EKG wave, just one cardiac cycle, and then I want you to label the following things on it. And usually one of the things I want students to label is where atrial contraction starts and where ventricular contraction starts. So relate the physical changes of the heart to the electrical changes. because they're not the same thing, but they are related. And oftentimes students will put that atrial contraction starts there. Is that correct?
No, it's
No.
the spot in front of it.
Exactly. So atrial contraction starts at the top of the P wave. And similarly, if you look at where ventricular contraction starts, does it start at the Q wave? Nope. It starts once the ventricles have depolarized. So they have to depolarize first, and then they can contract. So there's, again, that difference between between electrical changes and muscular changes. So that's an important piece to understand, is when you look at your book, it's going to show you various drawings of the heart. And specifically in that pie-shaped diagram, it does something like this, where it shows you, and I'm going to draw a really quick and dirty drawing of the heart. Shows you something like that, where you've got some atria and some ventricles, and I'm not going to draw the great vessels, but what it often does is draws depolarization as some kind of sort of like highlighting, where it starts over here in the SA node, and then in the next picture of the heart, the colored area representing depolarization has spread. And then after the spreading has completely taken place, then you start to see the ventricles squeezing inward. So your book is illustrating in a different way than I chose to, but it's the same thing. So they're showing you the traveling wave of depolarization, and then after that, they're showing you the ventricles, or the atria, excuse me, contracting. So what they're trying to communicate to you is the same thing that I did here, which is just that although depolarization happens before contraction, one causes the other. So the contraction that you see of the chambers is caused by the depolarization of the contractile cells. Does that make sense? Do we have any more questions about that?
That makes sense.
So you still need to be able to tell me on terms of the whole heart, what happens when. So SA node depolarizes due to the gap junctions. That depolarization is able to spread to the contractile cells. Once the contractile cells have depolarized, then we get atrial systole. And while that is finishing up is when the nodal cell signal is delayed at the AV node. And once the atria have finished contracting and they're on their way to repolarizing and entering systole, then the impulse is able to shoot down the interventricular septum and then turn around and head up.
And was that the delay that I was getting stuck on?
Yes, you were getting the nodal cell signal delay mixed up with the time between depolarization of a cell and its own subsequent contraction.
Okay.
Does what I just said make sense?
Yes.
Cool. Okay. Yeah, because there's a delay in both, but on different magnitudes. For any cell that I excite, if it's a muscle cell, there's going to be a short time where I've already stimulated it to begin depolarizing, but a few milliseconds will go by before that means calcium is released and excitation contraction coupling commences. So that's one delay. And that's a really, really zoomed in delay. It's talking about a delay within one cell between when I poke it and when it jumps. On a whole heart scale, there's a delay where electrical changes followed by contraction have successfully overtaken the entire top part of the heart. But due to the AV node's permeability difference to ions, the carrying of the nodal cell signal down to the bottom story of the heart, let's call it, is just held up for a minute. And that's not the same delay as the first one I mentioned.
So every time the EKG down here, every time you see a peak, that's when things are contracting. And then
not necessarily, because that would imply that something was contracting in the middle of the T wave, and that's not true.
Okay.
So only for the P and the R. Because the T wave represents what?
That one, I was just about to look it up in my notes because for some reason it's not coming to me offhand. Indicates repolarization of the ventricular contractile cells. So the ventricles are repolarizing.
Exactly. And what you end up seeing is that diastole begins kind of around there. So a little bit after.
Oh, okay. Oh, that's why it's an atrial diastole. Okay.
So I have got a wave for atrial contraction and depolarization. I've got a wave for ventricular depolarization. And I've got a wave for ventricular repolarization. So what's missing from this picture?
Is it the QRS?
No, I have that. That's seen here. I'm saying, so for the atria and the ventricles respectively, I've got a wave corresponding to atrial depolarization. That's this one. I've got a wave corresponding to ventricular depolarization. And then I've got a wave corresponding to ventricular repolarization. So what's missing?
Is it the atrial repolarization?
Bingo. So it's not possible.
Lecture.
It's not possible that the atria don't repolarize, because that's how the membrane resets to do this whole shebang over again. It's just that if you look at the amplitude of the QRS complex, it's really tall, right?
Yeah.
And if you look at a heart, you'll see, oh, the ventricles are not only a lot bigger, but they're also a lot thicker walled than the atria. So it's not the case that the atria don't repolarize. It's just that the signal from the ventricles depolarizing is so big that it swamps out the atrial repolarization. So you just don't see it on the EKG. It's not that it's not there, it's just hidden.
Okay. Yeah, I remember you talking about that too in the recording.
So here's the tricky thing about the EKG wave is I've never seen a text that does a good job of this unless it's an electrophysiology text, and that's like its own whole thing. So I show you a lot of diagrams that look like this, where I have an axis, and then this is usually time in milliseconds, and this is millivolts. And then I give you something that's like, I don't know, like this. Or maybe it's that. Doesn't really matter what. Your book never mentions how these graphs are generated. You don't know anything about that. So you know, like 0 is somewhere here. This is positive 30 millivolts. And then we've got like negative 90, negative 70, negative 60 is usually a threshold-ish. So you see, ever since 241, when we start talking about neurons and skeletal muscle, you keep seeing this chart with these numbers in the negatives and positives and milliseconds, and then you get these waveforms. But nobody ever tells you how those things are generated. Which means that when I then give you that, and I'm using this waveform to talk about depolarization and repolarization, it's natural to assume, and this is the underlying student assumption that I see, and it's not students' fault because no one ever explains this to them, that waveform is generated using the same technique, same measurement technique as this is. But that's not true. So the reason that this gets students fouled up is because they ask me things like, okay, so I've told you that this part of the P wave is the atria depolarizing, and then once they've depolarized and the peak reaches its crest, then we get contraction. So that makes sense, right? Because we got depolarization first, that's one, and then contraction second. And then I have the same thing for the QRS complex. So here we have the ventricles depolarizing, that's one. And then the yellow line represents when they start contracting, and contracting is step 2. So they're like, okay, so up is depolarizing. And if up is depolarizing, then how can this mean ventricular repolarization? If I've trained you to assume that up is depolarizing based on this thing. So students are like, huh? And that confusion is based on this assumption. So I'm going to draw a picture for you of how these charts are generated so that you understand why for the EKG wave, you can't make those same assumptions. So in order to get this picture, and let me just draw a contractile cell potential just for funsies. So in order to make this picture, you have a single contractile cell membrane, and you have a glass electrode that looks like that. And the glass electrode is poking through the cell membrane. And this electrode is connected to a measurement device, and it measures ions. So during this part of the curve, when sodium is going in to the contractile cell membrane, the sodium that is going in is also going into the electrode, and that's causing the electrode to detect an increase in positive charge. And so the electrode is attached to a measurement device and a computer, and the electrode draws this part of the curve. And then later on, when calcium is coming in during the plateau, same deal. So calcium is entering to keep that plateau steady, and some of that calcium is entering the electrode, and the electrode is saying, oh, well, the membrane is holding steady at a positive area because the calcium is being measured, and so it draws that part of the curve. So the way that all of these diagrams, action potential, pacemaker potential, contractile cell potential, the way that all of those diagrams are made is the same thing I just drew, where you're taking a single cell and you're measuring its membrane only. And that is why for this drawing, if the line is going up, you can assume that it's depolarizing. So here's how you make an EKG. And if you've ever been to the hospital and had an EKG done to you, or you've watched it be done, you'll know that there's a machine and then there's a bunch of leads with sticky things and they stick stuff all over you, right? That's what 12 lead EKG is. So the way that an EKG works is with 12 leads coming in 6 pairs, and within each pair, there's a cathode and an anode, so a plus and a minus end. So one pair is going to look through the heart from one angle, from negative to plus. So this is one pair of electrodes. And then there's another pair that's stuck at some different body position, and this is going to look at a different angle of the heart, so maybe from the bottom up. And eventually you get 6 pairs of these plus minus pairs stuck to you at different positions so that you're looking at electrical changes across the entire heart from a particular angle. And then again, those are attached to wires. The wires go into a computer, and the computer, based on its calculations from all of those electrode pairs stuck everywhere, and if you do a true 12 lead EKG, you know, like one of those electrode cathode anode pairs is stuck to your arm or your wrist. Others are on your chest and your back. They're all over the place. The computer does some fancy computing and spits out that, which is all of the electrical changes across all 6 pairs of leads happening in sequence, which is much different from measuring a single cell's membrane behavior. So although both the millivoltage charts and an EKG trace show electrical changes, they're not showing electrical changes at the same level. So this is showing electrical changes of the entire heart, including the nodal system and the contractile cells. So that accounts for the reason why you can't assume that the up part of this means depolarization. It doesn't, because it's concerning a different pair of electrodes. So that's the confusing bit. And I feel like that is what is missed by a lot of students, because they just naturally assume that the depolarizing, repolarizing chart is always the same forever. And then when I confront them with an EKG, they're like, my brain doesn't work that way. So that is why. And we're done recording. Stop recording.